Hi guys, so I'm in a fairly good mood today, so you're gonna get a nice video. Today's video is gonna be on something very important. It's a method to solve any f equals ma problem using, well, I've devised a method, right? So method for solving force problems. Okay, and I'm not sure if this method works for all problems, but for the problems that we're concerned with, like the not so easy problems, but not terribly hard problems, it works perfectly fine. So this is the method. Now, the first thing you always want to do, you see a problem. It might be overwhelming to you, right? You might not know where to start. You might not know what to do. But the first thing you do is draw all the forces. So draw all, keyword all, draw all the forces. And this is including gravity, right? Gravity is one of the easiest forces because you already know it. It's the same all the time. mg, 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 right? It's very easy. You draw all the forces. That's very important. Step 2, after you've drawn all the forces, you might still be overwhelmed. You see this problem, you're like, okay, Josh told me to draw all the forces. I've done that. But now what? The second step is probably the most important step. The second step is to use geometry. Use trig/geometry. And in this step is where you label all the angles, all the alternate interior angles, all the adjacent, the opposite angles, all that sorts of stuff, right? You know, like in the inclined plane problem, you have a plane and then you have theta, but you also have, let's say this is mg down, you also have a theta over here. You have, well, let's see, you have a theta here, you have a theta here. Draw all the angles that are related to the problem is what I'm saying. Okay, it's going to give you a better intuition in what to do. So step 1, you draw all the forces. Pretty easy. Step 2, you use geometry to find the angles. And step 3 is to split up. You have these angles and these forces, split up forces into components. Okay, pretty self-explanatory, right? We have, let's say, we have a force that's at an angle of alpha above the horizon, right? Let's say we have this kind of force, and then this is alpha, right? The step 3 is telling us to split up these forces into their components. So we're gonna have f cosine alpha and f sine alpha, right? We split it up into the components because we cannot work with this f. That's meaningless to us. But we can work with the components of f in the x and y directions. And you might ask, why can we work with this? Well, that's the next step. And the next step, the last step, is to use f alpha equals ma alpha to find, you use this f equals ma to find, how should I say it? To find accelerations, to find acceleration. There we go. To find accelerations and velocities, etc. Okay, so this is a pretty straightforward procedure, but it is a very important one. And if you use this kind of procedure, I'm going to show you a bunch of examples, but this is the main thing. So step 1, you draw all the forces. You have a problem. You draw the forces acting on the body. You can have multiple particles, right? You can have 1, 2, you have to draw m1g, m2g, and etc., right? You're going to have to draw the forces on every single body of this system. That's number 1. Number 2, you use geometry. You find the angles. You find alternate interior. You find opposite angles. You break the problem down. Step 3, you split up the force into components using these angles. You split up the force into the x, into the y. You could even split it up into the radial direction if that's convenient for you. Oh, and for step 3, when you split it up, you want to make sure that it's convenient. It's very important. And convenient, what does convenient mean? So for example, I have a circle, and I have like a force like this. Okay, that's just an example, right? And then let's say that this is my angle. This is the horizontal, and this is my angle, theta. Okay, so convenient. I have my angles, step 2, complete. But now, how am I going to split up this force? Do I split it up into the x and y direction? But what do I do? So in this problem, it's like it's a circle. So it's much more convenient for us to split it up into the radial directions, right? F in the radial direction and F in the theta direction, the tangential direction. It's much more convenient because we're working in this polar coordinate system. It would be meaningless to split this up into x and y because it just has no purpose for us because we're working, as I said, in this circular polar coordinate system. So whenever you're splitting up into components, you want to make sure that when you're splitting it up, it's going to be convenient for you. That's the main takeaway, so convenient. Okay? And then lastly, use F equals ma on every alpha. Alpha is just the parts of the system. So if you have two bodies, right, you have an incline and you have a block. You would have F1, which is the force on the incline, and you would have F2, which is the force on the block. So it's just F alpha. Okay, so this is the main, I'll leave that there. So this is the main procedure. Now let's do an example. We'll start with a relatively easy example. So, example 1. Example. Okay. Let's start off with something easy. Let's just consider a pendulum. A very simple pendulum. Okay. We have a pendulum. And it's displaced by some angle theta. Okay. So this is theta. Now, step 1. What was step 1? Draw all the forces. What are the forces here? Well, we have an mg down, force of gravity, and we just have a tension. Those are all the forces acting on the body. Okay, there are only two forces. Some people might mistake it that there's a velocity. Sure, there is velocity, but velocity is not a force. Tension, force of gravity, is a force, however. Okay, step 2. We go in detail. What's step 2? Step 2 is to use trigonometry. Okay, so let's go in detail. Let's sketch this. Let's make this bigger. So we have this blob over here. We have the force of gravity, right? mg. And we have tension over here, T. Okay, but what else do we know? Well, tension is along this direction. And along this direction, as you notice, there's this angle theta, right? And what else do we see? Do we have any alternate interior angles here? Yes, we do, right? If I extend this mg, notice these two angles are alternate interior angles, right? This is a vertical line, this is a vertical line, and this is a line crossing them. So the alternate interior angles, they're going to be equal to each other. Do we have anything else? No, that's fine, right? So you zoom in and you find the angles. Okay, great. Step 3, split up the forces into components. Okay, this is pretty self-explanatory. You have a tension, and then this is going to be T, and then it's adjacent, so it's cosine theta. And then we have, of course, T, sorry, it's a little sloppy. We have a T times the sine of theta. Right? Okay, great. Now the last step is use F equals ma to find accelerations and velocities. Okay, so let me just draw it over here. We have T sine theta, and we have a T cosine theta. Great. Oh, sorry. T, look, I'm making a beginner mistake. T cosine theta is going upwards, right? Look at the diagram. So T cosine theta. Okay, so those are our forces. Now we sum the forces, F. This should be a sum over all alpha. So the sum in the forces in the x and y directions. So x direction first. What do we have? We only have 1/4 in the x direction. Oh, and it's also very important to label an inertial reference frame. What is an inertial reference frame? An inertial reference frame is a frame that is not moving at all, or that's moving at a constant velocity. So we can say over here, we only have 1/4 here. And then we have this inertial reference frame. We call this the origin, O. So why would we call that? It's not moving. It's just a stationary point. It's very convenient. So this is going to be the positive direction, and this is going to be the positive. So positive x, positive y. Great, now we're ready. We have a t sine theta in the left. So it's going to be negative t sine theta equals m, and then acceleration in the x direction. And I write that using x double dot. And as I said, x double dot is the second derivative of x with respect to time. It's just the acceleration in the x direction, right? It's more convenient for me to write it this way because I can visualize it a little better. If I have vx, ax, and just x, it's not as nice as writing x, x dot, double dot, and x dot. This looks better, right? It's much nicer, much neater notation. Okay, so mx double dot. That's in the x direction. Now in the y direction, what do we have? We have, since the y direction is upwards, we have a t cosine theta minus fg, which is just mg, equals my double dot, right? The acceleration in the y direction. Okay, great. We did it. We found the equations of motion in the x direction and in the y direction. Now all we gotta do is solve. So I'm gonna make some approximations here, okay? And I'm gonna make some valid approximations. Let's zoom in a little bit. I drew the trajectory here for the pendulum, and you can see that for this pendulum is going mostly in the x direction, right? It's going this way and this way. It's barely going down, right? So we can assume to some order of approximation. So approximation, we can assume that y double dot is 0 to some degree, right? Because think about it. Look at this distance that it goes in the y direction versus this distance that it goes in the x direction. It's about 1%, the y as compared to x. It's pretty negligible. So that's why to a certain order of approximation, we can say y double dot is 0. Okay, so now what does this boil down to? We're just left with this. T cosine theta minus mg is 0. And thus, therefore, if you write 3 dots like this, it means therefore t is equal to mg times the secant of theta, right? I bring this over to the other side and I divide by cosine. Great. Let's keep going. Let's look at the x. Let's look at the x equations of motion. Negative t sine theta is equal to mx double dot. Great. We have the acceleration, but as a function of theta. We don't really want that, right? We want the acceleration as a function of time, and theta itself is a function of time. So, and tension, furthermore, is also a function of time because tension is dependent on theta. So how can we get this a little more neat looking? Now, let me just draw this one more time. We have this pendulum, and we have this theta, and let's say the length of the pendulum is L. So what's x going to be, right? This is the splitting up into components again. We should have done this. Well, it's my fault mostly. I should have done this in step 2. Remember, you used trigonometry. I thought that we were done when we split up the forces. But there's more to the story. This is going to be L sine theta, right? We split up the length of the pendulum into its x and y components now. And this is going to be L cosine theta because it's adjacent. Okay, so now we know what sine of theta is. That's awesome. What's sine of theta? Sine of theta is just going to be x over L, right? Opposite over hypotenuse. Sine of theta is going to be x over L, and of course equal to mx double dot. Now this is the key step. This is the key step. Sine of theta is equal to x over L. Because now watch this. What's tension? Well, we know tension. Negative T. Oops, what am I doing? Negative mg secant theta times x over L is equal to mx double dot. Let me bring this up here. And now watch. What's secant theta? Secant theta is just 1 over cosine theta. Right? And now, here's the big picture. I'm going to make another approximation here. I'm going to assume that theta is small. Alright, if we assume theta is small, then we can say that sine of theta is approximately theta and cosine of theta is approximately 1. There are many ways to prove this, but I'm just going to tell you that this is the case. For small theta, remember this is an approximation. So that means that this term, 1 over cosine theta, will be approximately 1. So that's it, we got it. Negative mg x over L, right, this just turns into 1, is equal to mx double dot. The m's cancel out, and we're just left with x double dot plus g over L times x equals 0. There we go. This is our equations of motion, right? All I did was add this to the other side. X double dot, the acceleration in the x direction, plus g over L, just a random constant, times x is equal to 0. And this equation has a solution. If you know how to solve this, or if you just plug it into the computer, you will get a solution. And the solution is that x is equal to a cosine omega t plus b sine omega t. Okay, that's x for you. So there we did it. And a and b are just random constants that we get from the initial conditions. And omega is defined to be the radical of g over L. That's the frequency of our oscillation. So now you probably wonder, where does this omega come from? It comes from this differential equation. Okay, so let's repeat from the beginning to make this nice and easy. Step 1, we drew all the forces. We had the mg and we had tension. Step 2, you use trigonometry as much as you can. Use the geometry of the problem to figure out what you need. We found the alternate interior angles, and as well we found the sine theta and the 1 over cosine theta, right, from this diagram over here. Step 3, we split up the forces into components, t sine theta and t cosine theta, because it's convenient to work with. And the last step is we used F equals ma. And in this case, we did an approximation, but usually you didn't have to do that. Because of this case is a case of the pendulum, and I didn't want to go too in depth on it. So for small angle approximations, we got the correct answer. So you just follow all 4 steps. Now let's do one more problem that's a little more complicated. So let me make a new page here. Whoops. And we're going to do a little, we're going to do a problem that's a little more complicated. Let's consider something like this. Let's consider a conical pendulum this time. It's a little harder. But as you'll see, if you follow this procedure, it's not hard at all. Okay, so a conical pendulum. Let me draw that a little better. Okay. So this is approximately the trajectory of it, right? And let's say it's going this way. And this is theta. Okay. So, first step. What's the first step? The first step, again, forces, forces, forces. What are the forces on this bad boy? We have mg down, force of gravity, and we have tension. Okay, great. Step 2, geometry. Geometry. Now let's zoom in on this man. Let's zoom in. We have gravity downwards, mg. What else do we have? We have a tension this way. Tension. And we have, if you draw the line for tension, we're gonna have this theta over here. So again, as the last case, we have alternate interior angles. Great, right? If you draw this line, this angle is gonna be the same as this angle. It's gonna be alternate interior. And let's say that the length of this is L. So now look at this, look at this. We also have this. And remember last time we forgot to do it, so let's be cautious that we do it this time. We have the length of this, so then this term over here, which you notice, this is the radius of the circle. So the radius is going to be L times the sine of theta, right? Trigonometry. And then this, the height, right? This is the height in the z direction. The z direction is just the upwards and downwards. So this is going to be the height that this circle is above the, below the starting point. So h is going to be L times the cosine of theta. Right. So great. We found the forces, we did the geometry. Next, components. What are the components going to be? So in the x direction, we're going to have, let's refer to this diagram, we're going to have a t times, what are we going to have? We're going to have a t times the sine of theta, right? It's going to be the sine of theta. And in the y direction, we're going to have a t times the cosine of theta, right? Pretty self-explanatory. Now, step 4. What is step 4? F equals ma. F alpha equals ma alpha. Okay. So let's do it. In the x direction, what are we gonna get? Okay, let's see. Is it wise to do the x direction in this case? Remember I was making a big point about convenience. We need to use coordinates that are convenient. So we have circular motion here. So do we really want to use x and y? It will be much easier to use r and theta, right? These polar coordinates, because we're working in the circular motion coordinate system. So in the r direction, in the radial direction, radial. Okay? Let's see, what do we have? We have a tension, t sine theta. It's in the radial direction, right? The center of our circle is here, and our particle is going like that. We're going to have a tension in the radial direction. But is it going to be positive or negative? Let's think about this. Well, radial is going to mean that the outwards, out of this circle, right? From the center of the circle is going to be the positive radial direction. So if something is going inside, it's going to be negative, right? Again, let me repeat this. Out is going outwards. So think about it, that the mass is flowing outwards, as an example. So if we're going inside, it's going to be negative. So as I said, tension is going into the circle, so it's going to be negative t sine theta. Okay, and is that it? That's all the forces. So by Newton's laws, force equals ma. So what's the acceleration? It's just v squared over r. Right? What's the centripetal acceleration? Okay. And the radius is not changing, right? You may know this, you may not know this, but actually centripetal acceleration goes by this formula. Oops, sorry. Minus v squared over r. This is the actual formula. Oh, sorry, it should be a negative. Centripetal acceleration is inward, so it's negative as well. Very important. So the actual formula for centripetal acceleration is this, which you write as x dot or whatever. So but the radius is not changing, so this is just 0. Right? If we have a problem where something is going down a cone, its radius will change, so you cannot neglect this term anymore. But I digress. This is going to be our formula. So what do we have? This crosses out, this cancels out. What's r? The radius of our circular motion. And remember, in the last step, we found r as L sine theta. So it's going to be T sine theta equals mv squared over, what's r? R is L sine theta. Great. That's the equation in the x direction. What's the equation in the y direction? Let's look at the forces. Okay, what do we have? We have a t cosine theta and an mg. So t cosine theta in the positive y direction minus mg equals my double dot. Now, what is the acceleration in the y direction? This is the y direction. We have a coordinate system like this. We have z, we have y, and we have x. Try to visualize that as three-dimensional, right? This is a right angle, and this is a right angle. So this is x, this is y, and this is z. Right? The z is going up out of the page. X is horizontal, and y is vertical. And they're all orthogonal, which means perpendicular to each other. If you hear orthogonal, it means perpendicular. So they're all perpendicular to each other. So our particle, our mass, is only moving in this xy plane. So it has no acceleration in the y direction. Just 0. So t is equal to mg secant theta. Right? You just multiply. And my notation is a bit sloppy here, because to be honest, gravity is going downwards. It's going in the z direction. So technically this should be mz double dot. So just know this, that my notation is a bit sloppy, right? Because listen, gravity always goes down, and the way we labeled the coordinate system, we said z, the z direction is up and down. So this should all be in the z direction, so this should be mz double dot. But if you want to write my double dot, no one will take points off. So great, we got tension, and we have an equation for tension here. Let's plug it in. mg secant theta sine theta equals mv squared over L sine theta. Okay, oh man, everything's canceling out. We have m's canceling out. Okay, that's it. G secant theta is the same thing as 1 over cosine theta. So sine theta over cosine theta is tangent of theta. And I'm going to multiply by L times sine of theta equals v squared. There you go. That's the velocity for you. And if you want to write it with square root, v is just square root of gl tan theta sine theta. You see, that was not hard at all. Let me repeat the process. Step 1, you draw the forces, right? We only have two forces, F, G, and tension. Step 2, the geometry. We look at the geometry of the situation. We find the alternate interior angles. We find the radius. We find the height. Very simple. Step 3, we split up the tension into components, T sine theta, T cosine theta. If there were more forces, we would split them up into components as well. And convenience. Step 4, we look at the convenience. We're working in circular motion, so we split it up into the radial and tangential directions. Okay. And then from that, we will get our equations of motion, and thus we can solve. And if you want omega, the angular frequency, omega is just v over r. But what's r? From our trigonometry, we see r is L sine theta, as I said before. So v over L sine theta, and thus we can put this into the radical. Is going to be a big radical. It's going to be bam gl tan theta sine theta. And if we put something in the radical, it's going to square it. So it's going to be L squared sine squared theta. Okay, and what is this going to simplify to? This cancels out with that. That cancels out with that. So, more things cancel out. Let me rewrite this a bit. G sine theta over cosine theta over L sine theta. Sines are going to cancel out. Everything simplifies, and we get that omega, the angular velocity, which is equal to theta dot. Not theta, we should write a different one. Which is equal to phi dot is equal to radical G over L secant theta. Right? Because we have a 1 over cosine, which is identical to secant. There you go. You found the velocity. You found the angular velocity. You have everything now. And that, my friends, is how you solve problems dealing with forces and alike. Thank you.